Now we are going to move right into looking at what the future is bringing. So I'd like to introduce Hea Nam, who is the project director for the NERSC 10 project. And then I think she'll pass it on to Rollin, who is the deputy project director for NERSC 10. So thanks so much. Take it away.
Libby, thanks for inviting us to present. Yeah, we're really excited to share with all of you about NERSC 10. It's been, I know it's, seems like it's saying, we had an exciting year, but this journey started at 2021. There's been a long journey of reviews and requirements gathering and talking to the community. So definitely the team, is excited about, where we are today, but we've been doing this for the long haul and there's still more time. Baking a supercomputer takes quite a bit of time, a lot of energy, a lot of effort, and as Kevin said, a lot of team science. So we're excited to share with you some of the activities that we've been going through. So yes, I'm Hea Nam. I am a user just like you. I started out, I come from the nuclear physics community. I actually was a NERSC user in my early days. I'm still now, but I was a NERSC user. I was also a user at Oak Ridge, trying to move, terabytes of data to run my, nuclear physics workflows at both facilities. So I understand the pain of, running on systems, moving data around, just trying to get your science accomplished in a good period of time. And so I can tell you that we've been listening. Doudna is that system. So the title of this presentation is NERSC 10, which is the larger project for Doudna, the system, a supercomputer for complex integrated workflows. And that's when you should say, what the heck does that mean? What are they really going to do to help me with my complex integrated workflows? We've been hearing about them. And now you're going to see, you're going to hear today about some of the steps we're taking to facilitate these workflows and make your lives better. All right. So on top of being a user facility and providing cycles to the Department of Energy Office of Science, one of the other missions that we need to balance that with to enabling your science is actually bringing in state-of-the-art supercomputing. So you can imagine that's hard because we listen to you and you're like, give me the most stable system on Earth. But at the same time, we are being asked to advance the state of the art. So we deploy new systems every 5 to 7 years because you're running these systems really hot. They're not going to last forever. So we've got to get the next one in, knowing that the existing one has to retire. We're helping you with your software environments. We want to couple very closely with your workflows. We know experimental and observational facilities have complex workflows. And also, it's not easy. So our staff are always working to get you onto the system, making it as easy as possible with our expertise. So in that mission, we have been responding to the DOE, and the DOE is really all of you. You are the ones driving requirements. You have science problems you want to accomplish. So, responding to the DOE means that we've been designing our systems in response to what the community needs. So you can see with NERSC 9 Perlmutter, we added GPUs, because if you look at the bottom, this is kind of how we see the growing workload. The workload, I come from the mod sim world. I love large scale simulations, but the reality is there's so much more opportunity with the changing workload where we can couple in AI and experimental data, which is really coming to fruition in the NERSC 10 era, right? This opportunity to create a seamless workflow that integrates all of these areas is very exciting for all of our, science capabilities. So, responding to this growing workload, we've been designing systems, and you're going to learn a lot more about that today. Rollin's going to come in and give you, a lot of details on it. And you can see NERSC 11 is on there. As Steve said, that's actually already on our minds. It takes a long time to bake a system. We've got to start working on NERSC 11 as well this year, next year. So what we do, in order to design a supercomputer, we listen to all of you. We do an extensive amount of requirements gathering. We talk to you. We also, see the reports that you're putting out into the community. We do lots of surveys. I know we keep poking and prodding you, like, what do you want? What do you want? And it's because we want to get it right. We want to make sure we're covering as many of your needs as possible. And so for NERSC 10, after all of that requirements gathering, it became very obvious that we needed to create a system that enabled you to have this integrated ecosystem for data analysis, real-time interactive feedback, the ability to search and analyze and reuse and combine data. Really, that was the three, the Venn diagram is really, to be able to do mod sim, large scale AI, as well as data analysis and capture that opportunity and make it so that you don't have to run ragged trying to get that all to work. So our mission statement, what we're driving towards as a team, is to accelerate your end-to-end workflows to enable new modes of scientific discovery. So what does that actually mean? That's a lot of fluffy words, right? We love fluffy words and marketing material, but we had to decompose that and figure out what does that really mean to the community? So really what these requirements are from complex workflows are that users want to interact with the system in new and complex ways. This is not your grandfather's supercomputer anymore. And I'm I would be the grandmother, right? I want to just SSH into the system. And every time someone says, oh, we have to do more than that, I say, why? But the reality is times are a-changing and users want to do SSH. They want to be able to interact via a Jupyter notebook. They sometimes don't even want to know supercomputers there and have just an API that makes things magically happen. They want to be able to use Spin to create their own services. You want to have the power in your own hands, as well as being able to create these very exciting services portals that open NERSC to your community, allowing you to upload data or spawn analysis from your communities without having to be a NERSC user or creating virtual organizations. So all of that is what we heard, and we said, we're going to enable that onto Doudna in a seamless way. On top of that, this workload is really complex. That means we've got to think about programming environments, how things couple together. Enabling this diagram requires a lot of complexity that we've been, as a team, trying to make sure that we can seamlessly enable for you. And then on top of that, you all want to go out into the rest of the world. So, there's a lot of data exchange that needs to happen, a lot of workflows that go beyond the boundaries of NERSC. And you'll hear some of that with Debbie's talk tomorrow morning about complex workflows. So you're complex, you want to do complex things, but it's because y'all want to do really cool science. So we're excited, as Jonathan said, we were able to announce our partnership with Dell and NVIDIA for our next system. We announced it in May, but it was a long time coming. And the date the date that is important to you all is that there will be early user access in 2027, because we still have a lot of work to do to bring the system into NERSC and get it online and continue our collaborations with our vendor partners. We're excited that we were able to name the system Doudna after Jennifer Doudna, the 2020 Nobel Prize winner in chemistry. So this is as much as we can tell you technically about Doudna until later. This is the money slide to tell you about the technologies that will be in Doudna. One is going to be 10x the performance of Perlmutter. It's going to be, have NVIDIA Vera Rubin CPU GPUs. It's going to enable AI and, compute optimized partitions. You'll have a high-speed interconnect. It will connect to the rest of the data center. There's going to be two types of storage, your standard platform storage and this new quality of service storage, and then something called workflow enablement nodes. And all of those details, Rollin's going to fill in for you. But the way that I like to look at this diagram is really that this is a supercomputer. Hopefully, we all know what a supercomputer is, right? So this is a supercomputer, and because the red box is really what you're accustomed to seeing. It is a supercomputer. It will run large-scale simulations quickly. It will, give you everything that you've expected in a supercomputer, high-speed storage. But there is an and to this because you're asking for the and. There's a lot more that the supercomputer is being asked to do now, and it has to be designed in from the very beginning. So Rollin will talk about the additional storage and why we would design an additional storage component, as well as instead of just your login nodes, and instead of spin sitting out there on a different, in a different cluster, how are we going to marry all of these? Because we want to make sure you have the seamless capability for your workloads. So it's tricky, and it's very, very exciting. But we're hoping that as we finish and implement everything, it will bring together new capabilities for you all. So here is your and, a supercomputer and. You can't just do the one anymore. All right. And then on top of that, we know you've got a lot of data in HPSS, CFS, you want to move data all over the place. So we also are working very hard to make sure that Doudna integrates very easily into our data center. And then on top of that, I know Sudeep said NERSC is people, but we also need a building. So as the NERSC 10 project director, I am also worried about this building because we need to make sure that it's ready to bring in Doudna. So this is if you take the tour, I hope you can appreciate, this building was created for an exascale supercomputer. And it is a very highly efficient data center, especially nowadays when we're talking about the power consumption and the increased data center workloads. We are very conscious about how we run our data center, how we design our data center, how we grow our data center. So we are increasing our power capabilities and our cooling capabilities in order to be able to have NERSC 10 efficiently run here. So please feel free to ask questions about the building. You'll see outside there was construction. If you noticed, I love watching the construction when I walk in every day. So you can see that outside they've been building, they've been removing soil today so that they can build this platform, which will enable air-cooled heat exchangers out there so we can reduce our water consumption. Because right now we use evaporative cooling and we want to be very good sustainability practitioners in our data center design. And on top of that, if you go down to the second floor to see the data center, you'll see there's been a giant containment wall that's been put up, tiles being moved around because we're doing electrical work as well as overhead work to be able to get ready for Doudna. This is a team effort across all areas of the lab. And with that, I just want to end, again, emphasizing what Kevin said. This is really team science. So at the left, you'll see the NERSC 10 leadership. Feel free to talk with us as well. I put in some of the leads in key areas that may be of interest to you. So there's system acquisition and build, workflow readiness, and technology integration. This is, of course, not everyone because it's pretty much, I would say, everyone in NERSC is involved in NERSC 10. But just so that you have some names and faces that feel free to ask us, talk with us. The ones in red are the ones who will be on the panel later today. So with that, I'm going to turn it over to Rollin because I know you're saying like she still hasn't explained complex workflows, and Rollin's going to do it.
Actually, what you said was you circled the part I was going to talk about and called it the tricky part. Right. Morning, everybody. I'm Rollin Thomas. I'm the Deputy Project Director for the NERSC 10 project. It's great to see all of you. I recognize many faces from previous engagements on previous systems, NESAP for data, the super facility, other projects that we've done together. So here I am today to tell you a little bit about what's going to be new in NERSC 10 on Doudna. What are the features that you're probably asking about during Hea's talk. So Doudna includes a number of firsts for NERSC and for its users. The first thing that I'll mention straight off is that it's the first NERSC supercomputer that we're bringing in collaboration with Dell. The last 5 generations of supercomputers at NERSC have been Cray systems, and this is our first Dell system. So we're really excited to be working with a new partner. They're very excited to be working with us. So we're having a lot of fun getting to know each other and building new relationships. This is going to be our first super chip architecture. It's going to be based on NVIDIA's Vera Rubin chip that has a ARM CPU in there. I'll have a slide on that because I think people will be curious about that. As Haya mentioned, there are going to be 2 integrated platform storage systems on the supercomputer. One that supports established workflows, like Scratch, like we have today, from IBM, and then another that is specifically designed to meet the needs of workflows that need consistent high I/O performance. So I'll have a slide on that as well. I also mentioned the workflow environment nodes. Think of these as login nodes plus spin plus plus. I have a slide on that. And then finally, all of the components in the system are going to be tied together using an InfiniBand network. So the WENs, which is short for workflow environment nodes, the WENs, storage, and the compute nodes will all be on this converged network. All right. Right? Okay. All right, so the first slide is just a slide to quell any trepidation people have about moving from an x86 architecture for the CPU, which is what we have done up to this point, to ARM. The good news is that a lot of work has gone into the software ecosystem for scientific computing on ARM. And that means that all of your favorite math libraries and things like that have equivalents in the ARM architecture, and you probably won't even notice. If you're a Python user, you're absolutely not going to notice because a lot of the providers of the underlying math libraries and scientific computing libraries that you use have transitioned to provide ARM variants as well. So there's a number of players in the space that have been moving to ARM chips because they're more power efficient. They provide more power and end-to-end capabilities for AI. So Apple, Amazon, NVIDIA, of course, and Google, they're all getting into this because they see this as the future. And so the software ecosystem has come along with them. So that's very good news for us. In addition to that, we have been doing experiments using an existing ARM system, a small system that's at our collaborators at TAC have given us access to. We've run all our NERSC 10 benchmarks there. We've been able to compile and build those, the tool chains that we need for those. Also a number of applications that we know are important to you. They have all worked fine. The only kinds of problems you might run into is if you're the type of user who gets in there and uses x86 intrinsics to accelerate your code on x86 hardware. People are smiling. You probably want to take another look at that. Okay? But one person ran into that problem, basically. Pretty straightforward. All right. Hey, also mentioned quality of service storage. And I remember that this was probably like the most hands went up topic at the last NUG meeting. So a lot of people were enthusiastic about the concept of quality of service storage. As Haya mentioned, we have discussions with users, requirements reviews, input from everybody telling us, what they like and maybe don't like about the file system options that they have at NERSC. And there are kind of 2 major things that stuck out to us. One is that there are workflows that have co-scheduled experiments going on, or they have stringent requirements for turning around analysis in a short period of time, and that they can't tolerate a lot of variability in the performance of the file systems. And so we went looking for options that would give users consistent quality of service performance on a file system, and we were able to unearth VAST and bring them into the system. In addition to that, VAST is actually marketing itself as a operating system for AI. And so it's designed in part to provide really good performance for AI training workflows, and of course, provide a consistent experience for users. So we're really excited to be working with VAST, and we're learning all about this new introduction to our ecosystem. And we're really excited to expose all of these cool features to you when the system comes in. Right. Workflow environment nodes, as I mentioned, this is like login nodes plus spin plus plus. So in the past, if you were on if you're an Edison user or like me, you were a Seaborg user way back, you were used to a really small partition of login nodes where you could compile code, you could edit your job scripts with VI and submit them. Maybe you could copy some data in and out, and that was just about it. So log out, come back tomorrow, see if your job ran. Today on Perlmutter, we have like a lot of login nodes. We have 40 login nodes. Each one of them has a GPU. On those login nodes, you can do all the stuff that you used to do, but in addition, people are running containers from the command line. They're composing Jupyter notebooks, developing code in IDEs. VS Code is super popular for that. Orchestrating services for data transfer and archive through Slurm, and also there's some form of workflow automation in the form of sProntact. So those are our login nodes. We have another thing at NERSC, which is a container as a service platform that allows users to run persistent services that support their community or their workflows that are running on Perlmutter. But it's got a brick wall between it and the login nodes. It's completely separate hardware. It's often another cluster, as Hea mentioned. That means that as a consequence, it doesn't see the platform storage, which is kind of a barrier to a lot of people who want to use Spin to manage and monitor their workflows. But nevertheless, it's super popular. It's maybe a little bit too popular in terms of what we've got available to keep it going, but it's based on Kubernetes. And again, as I mentioned, it's external to the system. So in the future on Doudna, what we're doing is we're combining these two kinds of sets of nodes together and enlarging it in order to kind of increase the capacity. So Spin in the future on Doudna will be integrated with the platform. It'll be tied much closer to it. It will be able to see both file systems that we've talked about. Users will be able to run the same kinds of services that they do there today. It's also the same infrastructure where we're going to be running Jupyter notebooks. And as I mentioned before, it'll be on the same network as the compute nodes and the storage subsystems. And it will have access to the same quality service storage capabilities that I mentioned on the previous slide. So on the right is kind of a airline seating chart picture that kind of depicts one way that you might carve up all of the resources in the WEN partition that we've got, combining user services that staff are running. All the green stuff is shell-based login that everybody SSHs in and does. The orange stuff might be Jupyter notebook nodes, and then some other services as well. We'll still be using something based on Rancher to manage all of this stuff in the future. Okay, so there's new stuff coming, new hardware capabilities, new software ecosystem capabilities, and we need to help our users transition to use this new system, use these new capabilities. We also need to do some work in terms of software engineering to make sure that using those tools isn't really hard, right? So NERSC is actually stepping in to try to fill the gap, make sure that things like quality of service storage are seamless and easy to use. So I'll start by talking a little bit about NESAP. Jack is back there. He's run NESAP in the past. Johannes and Neil are somewhere around. They're running NESAP today. So NESAP is our vehicle for preparing users for new systems. It's a collaborative effort between NERSC, science teams, and the technology vendors in order to prepare workflows for the new systems. This involves science application and technology co-design, so kind of a feedback loop between the NESAP teams who are working with us, sharing their workflows with us, teaching us about their problems, and what kinds of software things need to be produced in order to make sure that their science applications operate optimally. Provides early access to new hardware. We work together to optimize and analyze code to make the most of the new architecture's capabilities. Also, we learn from each other, so we embed postdocs in some of the projects, and we get together and we have hackathons, and it's extremely instructive to both sides. At the end of the effort, we take all of the lessons that we've learned, we turn it into documentation, training, things that we share out to the rest of the user community in order to bring the benefits to everybody and help educate the entire community. So it's been a very successful project in the past, mostly focused on performance and optimization of applications. And so as Doudna is kind of a change from the previous system, NESAP needs to change as well. Right, so that's what this slide is depicting, is that if you go back to NESAP for Cori, that was our first mini-core system, and so we focused on getting applications over the mini-core hill. And then Perlmutter was the first system that we had that had GPUs on it, and so a lot of the effort in NESAP was about getting applications ready and transitioned over to use GPUs. With Doudna, we have CPUs and GPUs as we did before on Perlmutter, but we have a lot more features there that enable complex workflows. So things like support for APIs, orchestration of services, configurable storage, and so on. So we realized that optimizing scientific workflows instead of just applications or specific kernels inside of an application requires looking at the entire technology stack and working at all different levels of that, whether it's I/O, how you're using the network, how your workflow is orchestrated, what services you're using, and how do you manage those. We just had the call for proposals over the summer for NESAP for Doudna. We received 168 proposals to join the program, which is more than twice the number of proposals we've ever had. We think that this is a pretty good endorsement of the idea of workflows for science, and that there's a lot of enthusiasm in the community for the concept of focusing on workflows. And so these are the 20 tier 1 selections that we'll be working with over the next few years in order to start the process of preparing users for the new system. So congratulations to everybody. We tried to give as much resources as we could to everybody. There's a few different tiers out there, and so at least most people are getting early access to the system. So again, thanks to everybody who submitted proposals. You made 60 people extremely busy from not just 60 people at NERSC. It wasn't 60 people at NERSC. It was at NERSC, at LBL in the computational sciences area, but also colleagues at other laboratories reviewed the proposals. And so it was a massive effort to get it all wrangled. There were lots and lots of spreadsheets. Right. NESAP is on Doudna going to be a proving ground for new workflow capabilities. So I mentioned that NERSC is going to be stepping into the software engineering space, creating capabilities that make the use of Doudna's new features more seamless, easy to use than they otherwise would be. And the NESAP projects that we're working with are going to help us do that. The NESAP projects that in their proposals have given us a description of the types of problems that they have, just how hard is it to do what you need to do today. And then we've identified in there opportunities for collaboration on key workflow capabilities that through previous round of interaction with users we've learned are going to be important capabilities. And so this is a kind of co-design effort. It's kind of virtual loop between workflow readiness, that is the NESAP effort, implementation, which is the software engineering, and then technology integration, which is a new feature of project deployment, of system deployment at NERSC, which is about evaluating, developing, and integrating new advanced technologies into the systems. That's an innovation in the project that I thought I would mention. So this kind of works together in order to advance everybody forward and provide new ways of running complex workflows on the system. So here's a big list of 5 different categories with a couple of different capabilities inside that are examples of the types of things that we're going to be working with NESAP teams to bring to fruition. And so we're kind of at the process where we're past the conceptual design of all of these capabilities. And so I'm going to give a slide on almost all of them. But the good news is it's got pictures, so it won't be like, you'll get really tired looking at it. All right. I've been an audience member before, so. Right, so the first one I'm going to talk about briefly is resource coordination, is the name that we've attached to this. But the basic idea here is to enhance the Slurm scheduler in certain ways to take advantage of the new hardware capabilities that are going to be available on Doudna. In addition, API endpoints, like if you're used to using the SuperFacility API today, anything that you do there that uses Slurm to coordinate or automate or submit workflows is going to be able to use these capabilities as well. So the simplest one to describe the capability in concrete terms is if you want to submit a job and you want to use the quality of service file system, and you want a certain amount of I/O operations guaranteed for your job, you'll be able to request that, and then through the implementation with VAST, be able to receive that. Okay, so you'll be able to say, my job needs this quality of IO service, and then it will be scheduled so that you'll be able to get that. Okay. There are other features that we might be expanding the capability to use, but this one's the easiest one to describe. Another intelligent resourcing capability that I want to mention, we call node partitioning and co-scheduling. Users are probably familiar with shared nodes. We have shared nodes. You can use one GPU instead of requesting all 4 GPUs on a system. This takes it a little bit further. So this allows users to say, run a workflow that uses only the CPU part of the node, and then a little bit of the CPU and some of the GPU simultaneously. So if you have 2 applications that are kind of talking to each other, one that only uses the CPU component, the other one using GPUs, you can do that in a nice way. The other thing that this does is it allows us to schedule CPU jobs onto nodes that are otherwise running mostly GPU-centric jobs. So that's what the picture kind of describes here, is there's kind of segmentation, GPU stuff to the right with a little bit of the CPU, and then another job on the left that's got just access to the CPUs there. Okay. The thing that this does is for individual users, it allows you to actually run the jobs, but for us as a center, it provides us a way to provide access to the CPU workload, CPU cores that would otherwise be inaccessible to users who could actually make productive use of them. So it's a more efficient way of using the supercomputer. Taya mentioned we want to use as much of the resource that we have available in the most efficient way, and this is something that will help us do that. At NERSC, we have first-in-class, best-in-class AI support. This is about hardening the ecosystem around AI, providing a seamless way for users to be able to do end-to-end AI training at scale. So here, basically, it's just making it easier for you to say, push a button, here's my data, and do an entire kind of AI training, get your model out. Okay, so I think people kind of understand the AI game these days. So that's just kind of like making it even easier. Also on the AI front, we recognize that people want to be combining AI simulation and data analysis into single workflows increasingly. There are a variety of ways that people try to shoehorn in AI into their simulation code. Some people have it running as a separate service. There's arguments about whether or not that makes sense. But there are programming challenges there that people want to like have the best performance that they can get from talking to an AI model, maybe that might be embedded in their application. So there might be some questions there around like some of our old friends like PyBind 11 and things like that that people may be going back to for this. So that's one of the efforts here. Containers have been something that NERSC has pushed for a while. We have a lot of users using containers on the system. We've engaged in the containerization effort in Linux for a very long time because we see the value of it. What we're talking about doing here is kind of finally committing to providing official NERSC environment container images where users can take those images, develop and run their scientific workflows either on our systems or on compatible systems outside of NERSC. This has been a challenge in the past because in order to build the NERSC programming environment, you had to include kind of proprietary stuff that you couldn't redistribute. So we've made different choices this time, and we've made it easier to be able to kind of move those containers out. So on the left, you'll see that we'll build the basic OS, compiler toolchain, communication libraries, and the IO and math libraries, put that into an image, ship it out to a registry. You can pick it up, you can from off of it, you can add your stuff on top of it, push it back to the registry, and then you can pull it to Doudna or wherever else you want to do it. So this, we think a lot of people out there have CI/CD pipelines that they want to run in the cloud, but they can't put NERSC in the cloud. So this is one way that they'll be able to do that. This slide basically is about putting spin onto the workflow environment nodes. It's basically running a container as a service platform directly on Doudna. So I think we've said that enough. So I think the idea here is pretty clear. This is also the infrastructure that will be used for running Jupyter. Cloud native workflows, if you're interested in Kubeflow or MLflow or any of these things, anybody? Okay, all right, a few people, okay. So that's one of the things that's not possible to do today on Perlmutter. We're interested in trying, they're figuring out who can work together. That's cool.
It does work. We're doing it right now.
We wanna talk
We
to
use
you.
ML flows.
Okay, great, awesome. All right, we want to talk to you about how we can make that easier.
Yes.
Because I don't imagine it's like just,
It's not.
yeah. Still have work to do. Okay. All right, so if you're into these things and you know, we've got other users that have asked us, you know, why can't I just run Kubernetes on your supercomputer? And, you know, we have this conversation. Here we're talking about trying to make that much easier. So these are things that people are used to using in the cloud, and then they come to HPC and they're like, why can't I use that thing? And why they can't. So this is about trying to make it so that you can bring that kind of workflow here with as few changes as you need to make as possible. There might be some things you need to do. All right, great. Quick one here about event-based scheduling. This kind of goes hand in hand with real-time computing, external events that need to happen that should trigger some kind of action here at NERSC. A real popular one is the file has finished transferring, submit the job. And so there's probably 30 different ways that people do that. This would be to provide kind of a native way that users could do this with, say, event message bus or features that are embedded actually in the quality of service storage platform itself. So use cases here are things like telescopes, microscopes, DNA sequencers that are outside NERSC but need processing resources inside. And you want to make this as seamless as possible. I think I've got two more. Workflow observability. Our focus has shifted from applications to workflows. That means that what are workflows? Workflows are a bunch of tasks in a graph. How do you, as a user, look at all that stuff and tell where the gaps are in your timelines? You need a tool that helps you. On top of that, it's complicated because you have your own workflow manager. Somebody else has their other workflow manager. Is it possible for us to instrument all of those things? No, not really. So this is kind of a dance that we have to figure out how to engage with workflows on in order to make it easy to be able to at least follow lifelines for workflows that consist of at least series of jobs and also interactions with services in spin and things like that. And so this would be a way to visualize where your workflow is having latency or bottlenecks, and also to provide metrics, what was happening on the node while my job was running, kind of stuff that we often get asked. The final thing that I want to mention here is the integrated research infrastructure. What I mean by putting this slide up is that we're going to demonstrate that we're actually a good player in the IRI infrastructure by demonstrating workflows that actually cross the boundaries of the center. So these are things that are all of the stuff that's listed here, other HPC systems or scientific instrumentation, the things that people do all the time and try to involve NERSC in. And if we can do this and it looks seamless, then we will consider job well done. And so that was a whirlwind tour of software capabilities that we're working on bringing to you to make Doudna more productive for complex workflows. There's going to be a panel after this. Some of the people who are working on this will be there and you can ask them questions about that. This is going to evolve also over the next year. You'll be hearing from us again, I'm sure a year from now, about how all this stuff has actually turned out and what changed and how things are going. I have a couple slides left about how members of the NERSC user community can engage with the project. One of the things that we do regularly is we have hackathons. The hackathons that are being kicked off in preparation for Doudna, they're going to be starting next year. Folks like Kevin, Helen, let's see, Helen. Okay, Helen's here. They're organizing those. Any team can apply. NESAP teams might get a little ahead of other teams that apply, but you know, they're always looking for teams. They're also always looking for mentors who can help out with these hackathons. So most of these hackathons have focused in the past on kernel performance and optimizing those things. So this is going to need to change for Doudna users to focus on other themes that are kind of listed here. So AI is a big part of it, co-scheduling complex workflows, opportunities for reduced precision, performance portability, containerization, and so on. So watch for those invitations. Another thing is that I mentioned NESAP. NESAP has a postdoc program associated with it. It's been extremely successful. The postdocs that have come through have gone on to do other great things. Some of them end up working at NERSC. Some of them end up working in industry or maybe at other national labs. It's a really great mission-driven kind of postdoc. So there's going to be job ads going out sometime later this week or next week, I think. And so if you yourself are looking for a postdoc position, or you know somebody that you would like to, recommend, they give it a shot, please send applicants our way. We need as many as we can get. All right. Okay, so I'm going to end up here, I don't know, a little early, but we can have some questions. Nobody complains if there's a longer break, right? So in conclusion, Doudna is, well, I'm going to say that the next generation of supercomputing we recognize is something that's going to extend beyond the boundaries of the supercomputer. This has been kind of transformative in our thinking. It's made it challenging to figure out how we take, you take those needs into account, because we recognize that we're not in a little box that that doesn't interact with the rest of the world. It's actually a part of the broader scientific enterprise of people's workflows that extend outside of NERSC. And so that's been, made the project really interesting and has unique challenges. Doudna is going to be a first of a kind supercomputer in a number of ways, and it's going to be the first NERSC supercomputer to be delivered by Dell. It includes a number of next generation hardware features that I've talked about here. And we're working on new software capabilities that are going to enhance and expose those capabilities so that you can make complex workflows more seamless. And we look forward to getting users on early in 2027. That's it. Do we take questions? Let me do all the questions?
Yeah, you can do it.
I'm the deputy. Any questions? I can't see online, so.
Yeah, I can check online.
Steven.
You're nervous? No. So I like the idea of the workflow environment nodes having more integration with the system as a whole.
Mhm.
At the same time, one of my most common problems is one person's workflow messing up somebody else's because they're hammering the login node and I can't LS anymore.
Yeah.
Those seem in tension. What are you doing to mitigate that?
Yeah.
Discuss.
That's a great question. So yeah, I'll tell you what we try to do today. So we use Linux C groups to try to put people inside of little boxes where if you try to use too much memory, you and if you try to use too much CPU on a login node, you just get really, really slow. Okay, so you just start to see worse and worse performance. However, users on the same node that you're on could be doing nasty things with the file system that everybody else can see. And so isolating that kind of stuff is pretty challenging. And so one of the things that we expect is that the quality of service storage system, we have users that are using, can put all of that stuff onto that file system, then everybody else will kind of have a better experience. It is a file system that does a good job at isolating one user from another. One of the common things that we hear from places that have done vast deployments and from the vast developers themselves is that this complaint you get about LS doesn't happen. Okay, I know I said that. I know you're going to think about that.
Can I record you saying that?
So far.
That's being recorded.
But we're hey, I made the slides. So yeah, so we're going to work on, we're obviously going to be trying to isolate people in that way. There are other tools that we have. I mentioned the capability, the co-scheduling and node partitioning capability. There are ways to isolate other performance things there besides just cores. There's memory bandwidth, memory. And then there might be options for isolating network traffic as well. But it is challenging because you are sitting there with all these other users. You'll notice that the number of boxes on the diagram, the exact number of those things may not be the exact number of nodes that we wind up with in the WAN partition, but it is going to be more than we have now on Perlmutter. And there's going to be different architectures we anticipate in the WAN partition to handle different use cases. So GPU users, people who are just using CPU nodes, and then of course services, you'll notice that they're all kind of separated from the other chunk because they're doing different things. So, isolating file system performance from file system activity of one user from another is pretty challenging with shared, but I think that there are going to be some exciting potential mitigations with the quality of service storage system. Is there a question on that?
There are two questions online, though they're from Paul Kent. I'm gonna ask one of them, but then we're gonna save the other one for our panel of experts. And so the question essentially is, is there gonna be like a test environment in particular with the new software environment so that users can, transition their work from the Cray HPE to, NVIDIA user software?
Yeah, so with regard to the programming environment itself, for a number of these other capabilities that we're working on, we will have the ability to deploy some of those capabilities on Perlmutter in advance of the arrival of Doudna. And so it won't be exactly the same thing. It won't be the exact same CPU and GPU architecture, obviously. But the tool chain and things like that, we have been verifying that we can put tool chains together that we can actually run on Perlmutter and we can hand over for users to use. In terms of opportunities for actually getting onto hardware that looks anything like what Doudna is going to have, we're thinking about ways that we might be able to do that. I mentioned that NERSC staff have been able to get on systems at other HPC centers to do a lot of testing. Those kind of opportunities may exist for users as well.
Great. Why don't we do maybe one more question and then I'll ask people to save their questions for our panel. So let's go ahead and we'll do one more.
Maybe this is better for the panel, but I was just going to ask about spin. So are you saying that spin is going to run on these WANs as well?
Yes.
So are there security concerns there or any concerns about external users overloading the WANs?
So Corey will be here to talk about that. He's on the panel.
Okay.
One of the things to know about spin today versus spin in the Doudna timescale is that spin, the production cluster, is 8 nodes. And so we're talking about a much bigger partition here available for spin resources. In terms of overloading though, we may look at ways to mitigate the number of workloads that are actually running that really need to be running versus things that are kind of like just one-off things that somebody stood up and abandoned. Security, you raised that question. That is something that we look at very carefully with spin already today. And so the same kind of questions and answers that we have for that, we're going to apply here as well.